Now, in our previous lecture we have defined the shift operator, the forward and backward difference operators. We have also defined the forward differences, backward differences. We have also derived the relationships between them. We have shown that given a difference table, a particular element in the table can be recognized as a particular forward difference or a particular backward difference, depending on where you want to use and for what purpose we are going to use particular data. Now, these differences are all related among each other. We would now like to show that these operators are also related to the divided differences that we have defined earlier, and a formula can be derived using the divide difference formula also. Let us now try to derive what is the relationship between the divide difference operator and the backward and forward difference operators. So, let us take it as relationship with divided differences. What we are considering is the equispaced data. We must remember that we are using the equispaced data, that is xi is equal to x naught plus I times h and I running from 0 to n. Now, let us write down the definition of the divided difference. First divide difference, f of x naught x 1 is equal to f of x 1 minus f at x naught divided by the distance between them x 1 minus x naught. Now, since this is equispaced data, x 1 minus x naught is 1 upon h. So, that is step length between the abscissa, and this is f 1 minus f naught. Therefore, this is equal to forward difference with respect to x naught. So, that is delta f naught divided by h, and I can also look as the backward difference with respect to x 1, that is I can also write this as backward difference with respect to h over. Therefore, when the data is equispaced, they are all equivalent, and the location of the divided differences or the location of the forward or backward differences can all be connected to this particular relationships. Now, let us take the second divide difference, f x naught x 1 x 2 is equal to f of x 1 x 2 minus f of x naught x 1 divided by x 2 minus x naught. Now, x 2 minus x naught is 2 times h, that is equal to 2 times the step length. Let us open this up. This is f 2 minus f 1 divided by x 2 minus x 1 is again h minus f 1 minus f naught, x 1 minus x naught is also equal to the step length h. So, I can simplify this and write this as 1 upon 2 h square, and this is f 2 minus 2 f 1 plus f naught. Now, I recognize this as the second forward difference with respect to f naught. So, I can write this as 1 upon factorial 2 into h square delta squared f naught, and this is same as the second backward difference with respect to f 2. So, therefore, I can write this as 1 upon factorial 2 h squared delta squared f 2. Now, I can proceed further and finally show that the nth divided difference x naught x 1 x 2 x n is equal to 1 upon factorial n h to the power of n, the nth forward difference with respect to f naught, or it is related to the nth backward difference delta n with respect to the last data item f n. Therefore, the relationship between the forward backward difference and the difference is given by this one. Interestingly, the these operators can be related not only among themselves, we can now show that they can be related with derivatives also. That is very important, because finally we would like to use these differences to construct difference methods for solving the ordinary and partial differential equations, wherein the relationship between the operators forward, backward or central with respect to the derivatives can be obtained. Then the derivatives in a differential equation can be replaced by the differences, and then we can find out the solution of the differential equation. So, let us derive with respect to the derivatives. Now, let us start with delta f x, the definition of delta f x. This is f of x plus h minus f of x. Now, let us expand by Taylor series the first term, that is your f of x plus h f dash of x, and the remaining terms I will write it as order of h square terms minus f x. Now, f x cancels with f x, I will bring this order of h square term to the left hand side and then divide by h. Therefore, I will have f dash of x is equal to 1 upon h delta of f x plus order of h. I have order of h square is divided by h, therefore, it will become order of h. So, therefore, whatever I have here is order of h term and delta f x divided by h. Therefore, we have the approximation for first derivative as 1 upon h delta f x upon f x, and because the error term is order of h, error is order of h, that is here, we shall call this as a first order approximation. Hence, we shall call this as first order approximation. Now, we know that the first forward difference is connected with respect to the backward difference. We have just shown that this is the equality. Therefore, I can now write down in terms of the backward difference also, but let us derive it separately again. Now, let us define what is our backward difference. So, let me divide the backward difference with respect to x. This is f of x minus f of x minus h. This time I will open this f of x minus h in terms of Taylor series. So, I will have this as f of x minus f x minus h f dash of x plus order of h square. Now, f x cancels with f x, I have a positive sign here. So, I will take order of h square to the left and then divide by h again. Therefore, I have got f dash of x is approximately equal to 1 upon h delta f x plus order of h. This is equal to this is equal to 1 upon h delta f x plus order of h. If I drop this error term, I have the approximation for the first derivative as 1 upon h delta of f x. Again, this is a first order approximation. Therefore, if I have a first derivative, say for example dy by dx, if I want to replace dy by dx by an approximation, I would simply write this as 1 upon h delta of f of x naught, wherever the particular point is being taken. Similarly, if I want in terms of backward difference, I can use the backward difference. Now, this result can be extended to higher derivatives. For example, I can start with delta squared f x and write this as f of x plus 2 h minus twice f of x plus h plus f of x. Now, I shall open this both these terms by Taylor series. So, this will give me f of h plus 2 h f dash of x plus 2 h whole squared by factorial 2 f double dash of x plus order of h cubed minus 2 times f of x, and this is h of f dash of x, h squared by factorial 2 f double dash of x plus order of h cubed. and the last term stays as it is plus of f x. Now, let us simplify this. This is f x, this is f x, 2 times f x cancels with 2 times f x. This is 2 h f dash x, this is minus 2 h f dash x, therefore, these two term cancels. So, the first non vanishing term is this and this. This is 2 squared 4 by 2, that is 2, and this is minus 1, 2 by factorial 2 minus 1. Therefore, I have left out with 1 as the coefficient, that is simply h squared f double dash of x plus order of h cubed. These two terms simplify to give us simply h square f double dash x. Therefore, I can write down the approximation for this is equal to 1 upon h squared delta squared of f x plus order of h. I have divided by h square, therefore, I will have only order of h over here. Therefore, I can write approximation as 1 upon h square delta squared of f x, and this is a first order approximation. This is a first order approximation because we have only order of h term that is left out over here. And by the same reason we can derive that f dash x is equal to 1 upon h square delta squared f x also, and this is also the first order. Therefore, if I have to use it in a differential equation, for example, d square by dx square, I can replace the d square by dx square by 1 upon h square delta squared of f x, or in terms of the backward differences. Now, you can immediately connect this with the divided differences. We have earlier derived the relationship between the divided difference and forward and backward differences. I can immediately connect all these ones with respect with the divided differences also. Now, we have derived one more operator, which was a symmetric operator, which we called it as the central difference operator. Let us now define the second central difference. That was defined as f of x plus h minus twice f x plus f of x minus h. So, this is the definition of the central difference. Now, I would like to open this up also by Taylor series. So, we will have f x plus h f dash of x, h square by 2 f double dash of x plus h cubed by 6 f triple dash of x plus order of h 4 minus 2 times f x, that term, plus the third term is f of x minus h f dash of x, h squared by 2 f double dash of x minus h cubed by 6 f double dash f triple dash of x plus order of h to the power of 4. We have just opened f of x plus h by Taylor series. We retain terms up to order of h cubed and then retain the error as h 4. F of x minus h also we expanded. Let us now simplify this particular right hand side. So, we have here f x combines with f x, cancels with minus 2 f x, f x plus f x minus 2 f x. This is plus h f dash x minus h f dash x, these two cancel off. Then we have h square by 2 plus h square by 2. So, the first non vanishing term is h squared f double dash of x. This h square by 2 h square by 2 combine. Now, you can see the odd derivative, this is plus h cubed by 6 minus h cubed by 6, it cancels again. So, what is left out is order of h to the power of 4 terms. Now, we may mention the reason why it has happened is this central difference operator is symmetric about this middle point. Since it is symmetric about the middle point, all the odd derivatives would cancel. This is h will cancel, h cube will cancel, h 5 will cancel in there. So, if I want higher order formula and take the higher order differences, all the odd derivatives would automatically cancel. Therefore, I can now write down f double dash of x is equal to 1 upon h square delta squared of f x plus order of h square. Therefore, this is approximately 1 upon h square delta squared of f x, and this is a second order approximation. Error is now order of h square. Therefore, this is a second order approximation. This is a second order approximation, which is one order higher than what we have obtained for the forward and backward difference. This is a basic property of the central difference operators. The order of approximation will be higher than we use in the forward or the backward differences. Let us now construct interpolating polynomials in terms of forward and backward differences using the divided difference interpolating polynomial. This formula is usually called as the Gregory-Newton formulas. As often it is also called simply Newton's formulas. That means, we may not attach the name Gregory, but we will call it as Newton's formulas. Let us first take the forward difference formula. The forward difference formula. The formula derivation of formula is just one line. We take the divided difference formula, and then we have just now derived the relationship between the forward differences and the divide difference. We just replace the divide difference by the forward differences to get this formula. So, let us write down what is that formula. We had written the divide difference formula as f of x naught x minus x naught f x naught x 1. Let us write down one more term. This is x minus x naught x minus x 1 into f x naught x 2 plus so on x minus x naught x minus x n minus 1 f of x naught x n. This is the divided difference formula that we have derived earlier. Now, I would just replace the divided differences that we have written here by using simply f of x naught x 1 is 1 upon h delta f naught. The second difference is 1 upon h square factorial to delta squared f naught, and finally, the nth divide difference is by this. So, we just replace these divide differences by the corresponding relationship with the forward difference. So, this will be f of x naught, this is x minus x naught, this is your delta f naught. Remember, this is f x naught x 1. So, it will be delta f naught by h here plus x minus x naught x minus x 1. This is the second forward difference delta squared f naught by factorial to h squared plus so on. The last term will be x minus x naught x minus x n minus 1 delta n f naught by factorial h to the power of n. So, we can just substitute the data points that are given to us, the forward differences from the forward difference table, just substitute it and simplify to arrive at the formula. Now, the error term would be the same because the interpolation polynomial is unique. Therefore, the error term that we get will be same as what we have proved in the Lagrange formula. So, let us write down the error term also. So, the error would be simply E n f x is x minus x naught x minus x n by n plus 1 factorial f n plus 1 of xi. Now, earlier in when we have derived this Lagrange interpolation and the divide difference, we have done some examples wherein we try to construct what should be the step length h that should be used in order that the linear interpolation has some error or quadratic interpolation has got certain error. Now, at that time, since we wanted the approximations say for M2 or M3, that is the maximum of f double dash or maximum f triple dash, we wanted the function that was actually being used there in order to have a bound for that one. But however, since we have now obtained the relationship between derivative and the differences, even if a table of values is given to us and we are not given the function that is approximating that particular data, we can still obtain an approximation for the required derivative when we are using the linear or quadratic interpolation. How do we do it? Let us suppose I am using only linear interpolation. Suppose I am using the linear interpolation, then the error would be E1, let us write down its magnitude also. The magnitude will be less than or equal to 1 upon factorial 2, 1 upon factorial 2. We are writing this as maximum of x minus x naught, x minus x 1 and maximum magnitude of f double dash of xi. Now, we have just now proved that the second derivative is approximately 1 upon h square delta squared f x. That means, I can now replace this f double dash by delta squared by h square. So, this will be less than or equal to 1 upon 2. The maximum of this we have proved that it occurs at the middle point, that is equal to h square by 4 we have shown, and therefore, this is equal to delta squared f naught by, we are writing this approximately, this is equal to by 2 h square also I should write. I am taking the expression from here, delta squared up h square upon h squared. Therefore, this is equal to h square, h square cancels with h square, I have 8 here, delta squared f naught in magnitude divided by 8. Therefore, if I have got a table of values and I am using linear interpolation using a particular 2 points, now I have got in that table available for me forward differences. Therefore, the approximation for M2 will now come from the data itself. Therefore, I do not need to have the function being specified when a data is given to us and we can use it. Suppose I am going to quadratic interpolation, what I will have here is a third derivative, and third derivative is we have shown that it is related to delta cubed f naught. So, I would just have to use the approximation of delta cubed f naught, and that will be an approximation for the linear interpolation or quadratic interpolation. Now, for computational purposes, this formula that we have written here can be simplified still further. For suppose in a given table of values, you are asked to just find the value or interpolate at the value a particular value, a number is given to us. Then it is not necessary for us to construct the entire polynomial, simplify the whole thing and then substitute x is equal to that value. We can just straight away substitute the value that is given to us and then simplify this straight away by using a substitution to simplify this further. So, let us see what the simplification we can do here in this formula. Let x minus x naught by h be equal to some value u. Let us put x minus x naught divided by h is equal to u. That means, I am setting x is equal to x naught plus u h. We remember that since we are now interpolating at a value larger than x naught, always u is a number which is positive number, u is a number which is positive here. Now, I want to substitute for this here. So, I know what is x minus x naught, let us find what is x minus x 1. X minus x 1 is by definition x minus x naught minus h, x 1 is x naught plus h. So, I can substitute for this. X minus x naught is u into h minus h, that is u minus 1 into h. Similarly, x minus x 2 or x minus x 2 is x minus x naught minus 2 h. So, this is equal to u h minus h, that is u minus 2 of h. Therefore, in general x minus x I is equal to u minus I into h. Now, you can just have a look at it before we write the formula. X minus x naught divided by h is equal to u. There is a factorial 2 h square here. Therefore, I will take this h with each one of them, x minus x naught by h, x minus x 1 by h. So, I would then have u into u minus 1 as the second term. So, I would just substitute these values here, then I would get this. Let us write down. P x can therefore be written as f of x naught plus x minus x naught by h is u delta f naught. This is u minus 1, u into u minus 1, h square has cancelled, divide by factorial 2 delta squared f naught plus so on, plus let us take this term, this is u minus 1, the last one is u minus of n minus 1 by factorial n. This factorial n is here and each one of them has got h, it cancelled. This is your delta n f naught. Now, you can see that these are nothing but the binomial coefficients with respect to u. Therefore, I could simply write them as the binomial coefficients and write in the simple notation summation 1 to n. I will use the binomial notation as u I, it is easier for me to write this one. So, I will use this notation u I binomial coefficient delta n f naught. So, it is simply the binomial coefficients with respect to u is a number here, u is greater than 0. So, I can just take it like u is equal to half say. So, we will have 0.5 minus 0.5 by factorial 2 and so on. So, I just write down the binomial coefficients, use these forward differences and have this solution immediately. Now, I am substituting for a particular x, therefore, u is determined. Now, let us see interestingly what will happen to error in this case. The error would be there is no h in the denominator, therefore, each one will contribute a h. There are n plus 1 terms here, therefore, it will contribute h to the power of n plus 1. Therefore, this is u into u minus 1, u minus n, the last term is n, u n minus 1 divided by n plus 1 factorial, that is here h to the power of n plus 1 f n plus 1 of xi. Now, this is the next binomial coefficient, this is u c n, the last binomial coefficient, this is u c n plus 1. This is simply your next binomial coefficient u n plus 1 h to the power of n plus 1 f n plus 1 of xi. Therefore, everything comes in terms of binomial coefficients and we can obtain the error term as well as the interpolated value at any point very easily from this. Now, the derivation of the forward difference formula can be viewed or obtained in a very simple manner like this. Let us just derive the alternative way of deriving this formula. Let us write f x as f of, I want to use forward differences. So, I will write this as x naught, x minus x naught by h, that is my u into h. You cancel off h, cancel off x naught, f x is equal to f x. So, therefore, I have written the argument as x naught plus x minus x naught by h into h. So, that I get back this one. Now, this is u. So, I will write this as f of x naught plus u h. This is the definition of u, therefore, this is simply. Now let us view this as a shift, that means shift operator. So this will be e to the power of u of f x. But we know that E is equal to 1 plus forward difference delta, that is 1 plus delta to the power of u of f x. F of x naught, f of x naught, here also x naught. Now expanded binomially, so what we had written earlier comes out immediately, that I is equal to 0 to n, the binomial coefficients u I is equal to, this is delta of I f of x naught, this is delta is here. So this is 1 plus u c 1 delta plus u c 2 delta square and so on. So this is delta I f of x naught. Therefore we get back the formula that we have written earlier by simply using this notation and this way of deriving the formula.
U may not be integer.
U is not an integer, even here also u is not an integer. For example, as I said, the first, let us say the data points initially say 1 and 2, 3 and so on. So I am now, let us say I am interpolating here at 1.5 I am interpolating, then by definition my u must be equal to x minus x naught divided by h. X is equal to current value is 1.5, x naught is 1, the h is equal to 1. Therefore this is equal to 0.5. So h will never be an integer here, because we are interpolating at an point in the table, the data points given, the data points itself may be given the step length, say not an integer, say some 0.1 or 0.01. So the step length itself is not an integer, therefore u is never an integer. Therefore the binomial coefficients would go on reducing, the starting with 0.5, then 0.5 minus 0.5 minus 1.5 and so on, but there will be denominator is factorials are coming. So the in totality each term as we go forward they would all be smaller and smaller and smaller, they are going to be reducing. Before we take an example, let us derive the same formula in terms of backward differences. So let us call this as Newton's backward difference formula, Newton's backward difference formula. Now we shall use this approach to derive it in just 2 lines, but we remember we are talking about the backward difference formula. So since we have got the data x naught, x2, xn, I must use the backward differences. So I will have to use them in the backward way. Therefore whatever I want to write, the argument should be in terms of xn, because I want to write down a particular, say a particular level you have taken x1 x2, I want to use backward difference with respect to this, I have to use the backward differences with respect to the last argument of this interval. So I will have to use in terms of xn, that means I will write this as f of xn plus x minus xn by h into h. Now let us set again u is equal to x minus xn upon h, then this will be f of xn plus u of h. But we note now that u is always a negative quantity, because x2 is the last point or xn is the last point and x1 is an point intermediate point. Therefore x minus xn is always going to be negative, therefore this is a negative fraction, it will be always be a negative fraction. Again we write this as in the terms of shift operator e to the power of u f of xn. But we have proved the equality of the operator E with the backward difference delta, and that is 1 minus backward difference delta to the power of minus 1. So that is 1 minus backward difference minus 1 to the power of u, that is minus u. this is a minus sign here, there is a minus sign here. So, this will be 1 plus u into delta. Let us open it up. This is plus minus u into, okay, let us write down minus u minus 1 by factorial to delta squared, and so on. We will write down the last term in a moment, operate on f x n. Therefore, they would all simplify as f x n plus u delta f x n plus u into u plus 1 by factorial to delta squared f x n. They would all be positive, because if when you are taking the odd, then there is a negative sign here. So, they are going to be plus sign. So, we will have the plus sign only, u into u plus 1, so on u plus n minus 1 by factorial n delta n f n. Where we note that u is a negative quantity, u is a negative fraction. Therefore, the error can immediately be written as the next coefficient, and the next coefficient is u into u plus 1, so on u plus n plus 1 factorial. Each term contributes a h here. So, h to the power of n plus 1 f n plus 1 of xi. Now, let us take an example combining all of them. So, let us take this example. Construct an interpolating polynomial, fitting the data x f x minus 2 minus 4 minus 1 1 0 0 1 minus 1 2 4 3 21. Now, to illustrate the use of the substitutions we made here, let us also interpolate directly. I want to use it directly, so that I do not simplify the formula and then use it directly, the values of f minus 1.5 and f 2.5. Interpolate directly the values of f minus 1.5 and f at 2.5. Now, in order to apply this, I need to first of all write my difference table. So, let us write down our difference table. X f x minus 2 minus 4 minus 1 1 0 0 1 minus 1 2 4 3 21. So, let us write down delta of f, the first forward difference, that is 1 plus 4, that is 5, 0 minus 1, that is minus 1, minus 1 minus 0, 4 plus 1, that is 5, 21 minus 4, that is 17. Let us go to second forward difference. Minus 1 minus 5, that is minus 6, minus 1 plus 1, that is 0, 5 plus 1, that is 6, 17 minus 5, that is equal to 12. Let us go to third difference. 0 minus 6, that is plus 6, this is 6, 12 minus 6, 6. Now, you can see all the other differences are going to be 0, even though we have a data, a bigger data. Therefore, it will approximate a cubic polynomial, delta cubed is non-zero, therefore, it will approximate only a cubic polynomial. So, let us write down our formula f x naught x minus x naught delta f naught by h, x minus x naught x minus x 1 delta squared f naught by factorial 2 h squared. We have third difference available. So, I must write down one more term x minus x naught x minus x 1 x minus x 2 delta cubed f naught by factorial 3 h cubed. Now, let us substitute the values. The step length is 1 here, minus this is step length is 1, h is 1, x naught x 1 x 2, and these are our differences. So, we are using x naught, taking this x naught as this, f naught is this, delta f naught, delta squared f naught, delta cubed f naught. So, we are taking these forward differences to substitute it over here. Therefore, we have here f of x naught is minus 4, x minus of this plus 2, that is 5, h is 1. So, this is simply 5, x plus 2, again x plus 1, the second derivative is minus 6 by 2, factorial 2 is here. So, I will write down 2. Third term is x plus 2, x plus 1, and third one is x minus 0. So, that is your x. Third forward difference is 6, 6 upon factorial 3, this is factorial 3, 6 upon 6. So, which you can simplify this, and I will give the answer for this. The answer for this is simply x cubed minus 2 x, x cubed minus 2 x. Of course, since you have simplified it, I could have used the, when I have been asked to find interpolate the values, I could have substituted there and get it, but I want to illustrate how you can get directly. Now, I want to find f at 1.5, I want to minus 1.5, this is your x is equal to minus 1.5. Now, x at 1.5 it lies between these two values. So, minus 1.5 lies between these two, minus 1 and minus 2 and minus 1. Therefore, I would write u is equal to, now I will take my x naught is minus 2, x naught is minus 2, u is x minus x naught by h, x is minus 1.5, x naught is minus 2, therefore, plus 2 divided by 1. Therefore, this is equal to 0.5. Therefore, this is 0.5. Now, we will use the forward difference formula. This is a forward difference formula, f at x naught, u delta f x naught, u into u minus 1, this binomial coefficients. Therefore, f at minus 1.5 will be equal to f at minus 2, let us write down the details, minus 2 plus u delta f naught plus u into u minus 1 by factorial 2 delta squared f naught. The third difference is also available to us. So, we will have u minus 1 u minus 2 by factorial 3 delta cube f naught. Now, f of minus 2 is given as minus 4, u is 0.5, u is 0.5, delta f naught we will take from here, that is your 5 plus 0.5 u minus 1 minus 0.5 by 2 into delta squared f naught is minus 6. Then I have the next term as 0.5 minus 0.5 minus 1.5 1 by 6 into 6. Now, this I will leave to you, this is simplify this is comes out to be minus 0.375 minus 0.375. Now, consider the second part of the problem. I want to find an approximation to f 2.5. Now, we notice, let us look at back to the table. 2.5 lies here, 2.5 lies here. Therefore, there are no forward differences available for me here. Therefore, since I am at the end of the table, I must use only the backward differences. So, I shall be using the backward differences with respect to this as these backward differences. I would go in the backward direction when I am at the end of the table. Therefore, I must now use the next formula that we have written it over here, that is the formula, this formula should be used, and therefore, our x n here is the last point, that is 3, our x is equal to 2.5 at which we have to find. Therefore, u is equal to x minus x n divided by h, that is 2.5 minus 3 divided by 1. This is equal to minus 0.5. As we mentioned, when we are going for the backward differences, u will always going to be negative. Now, let us write down the solution. Therefore, f at 2.5 will be equal to, I will just put this slide here and from here let us write down. Therefore, now the formula would be f of x n, will substitute the values u delta f x n plus u into u plus 1 by factorial 2 delta squared f x n, u into u plus 1 into u plus 2 by factorial 3 delta cubed f x n. Now, let us substitute the values from this table over here. So, this is f at x n is 21. So, this is equal to 21, u is minus 0.5, u is minus 0.5, the backward difference with respect to this is 17, minus 0.5 u plus 1, that is plus 0.5 delta squared f x n, that is 12. Then we write the next term minus 0.5 plus 0.5 u plus 2, that is 1.5 1 upon factorial 3, and this backward difference is, third difference is 6. So, we are using this. Now, we can simplify this and the value of this comes out to be 10.625. Therefore, if we are at the end of the table, there is no alternative but to use the backward differences. If you are at the start of the table or later, we can always use the forward differences, and the sometimes we have not derived the central differences using central differences. If you are at the middle of the table, we can try to use the central difference table, but however, even if you are middle of the table, sufficient number of forward differences are available or backward differences are available, I can use any one of them. For example, if I am here, if I want to have a value over here, there are sufficient number of forward differences here, I can use it, or I have sufficient number of backward differences that are available to me. So, the choice is up to me whether I want to use the forward differences or backward differences when both of them are available for me. Okay, we will stop at this one.